Hello everyone, it's my pleasure to present our work here. I'm Jing Feng, a third-year PhD student from the University of Hong Kong. The talk is about a new graph contrastive learning paradigm for recommendation, formerly named NLGCL, Naturally Existing Neighbor Layers Graph Contrastive Learning for Recommendation. First, I will give a very brief introduction about graphing recommendation. So everyone knows that user-item interactions can build or formed as a user-item graph, like this figure. The left one can be formed as the right one. And then let's move on to talk about the graph contrastive learning. So why contrastive learning are useful? So everyone knows that one of the most important problems in recommendation is data sparsity problem. And contrastive learning has gained attention in this field for its effectiveness in mitigating data sparsity problem. And naturally, user item graph can make graph contrastive learning be a positive and popular paradigm in recommendation. And all existing graph contrastive learning can be summarized as two steps. First is augmentation, and second is contrastive learning. For augmentation step, we need to build one or more contrastive views through some operations like feature perturbation or structure perturbation. And then in the contrastive learning step, we adopt the contrastive learning laws like InfoNCE between the contrastive views. But there are some limitations in existing GCL's paradigm. So first is about efficiency. So most existing GCLs need to build one or more contrastive views and storage them, so it will need additional storage overhead. And second is effectiveness. Some augmentation process include operations like feature perturbation or structure perturbation, and this will lead some task irrelevant noise. So can I find or build a new paradigm which can address this or mitigate or addresses these two challenges? For graph learning, I think it's no. But for recommendation, I think we can find a new paradigm. So first, most existing GCL methods in recommendation are directly moved from the paradigm in graph learning, and we need to analyze the difference between recommendation and other graph tasks. First, for recommendation field, users and items with interactions share partially similar semantics, so we can treat all edges in user item graph as positive edges. But for other graph tasks, like we just use node level graph tasks as an example, some agent nodes may have different labels. You can say the red edges represent the connections between two nodes with different labels, and green edges represent connections between two nodes with the same labels. And also for another type like edge level graph task, it also not all edges in this task are positive. So one advantage in recommendation is all the edges are positive. Then we talk about the message passing process in user item graph. For simplicity, we refer to the atom node pointed by the blue arrow as atom I1, and the users pointed by the red arrows as user U1 and U2 respectively. And we can see the message passing between L's layer and L plus 1's layer. In the L plus 1's layer, the representations of nodes U1 and U2 are aggregated based on the L's layer representations of atom I1 and other atom nodes that have also interacted with U1 and U2 respectively. And also in recommendation systems, we based on assumptions that users who interacted the same atoms may tend to have similar preferences, and also atoms interacted by the same users often share same properties. Based on this assumption and the message passing process, we can find that the representations of atom I1 at layer L and the representations of its neighboring user U1 and U2 at layer L plus 1 can be formed as positive pairs in contrastive learning. But for other graph tasks, it cannot be, these positive pairs cannot be found because the neighbors may have different labels and not all the edges are positive. So actually, we already talked about the positive pairs in our NLGCL in previous slides. So in this slide, we will give an overall paradigm for our NLGCL. And our NLGCL include two different scopes. First is heterogeneous, and second is entire. The difference between these two scopes only about the negative samples, negative pairs. So let's take user U as an example. For the representations of user U at layer L, the L plus 1 layer representations of the item it interacts with are considered positive pairs with user U. These positive pairs are suitable for both scope, but for heterogeneous scope, the L plus 1 layer representations of all other atoms are considered negative pairs with user U. But for entire scope, the L plus 1 layer representations of all other nodes rather than only atoms are considered negative pairs with user U. And we summarize the positive pairs and negative pairs for all the scopes in the left lower table. Actually, for the contrastive learning stage, we directly use the InfoNCE as our contrastive learning laws. But maybe someone has already found that there are differences between NLGCL and existing GCL-based paradigm. Is all existing paradigms work only have one positive pairs, and NLGCL have multiple positive pairs. So we just arrange them at first and then adopt InfoNCE. So maybe some future work can explore some weighted methods, but I think average is simplified and good enough. And then we move on to the experimental results. We can see that NLGCL consistently outperforms all baselines across 4 widely used datasets. And for efficiency study, actually similar to other GCL-based models, NLGCL can also reduce the number of epochs required for model convergence. And also, since NLGCL do not to build and store some contrastive views, so NLGCL achieve better efficiency than all GCL-based baselines. And we talk about the ablation study. Surprisingly, we observe that NLGCL with heterogeneous scope consistently outperforms NLGCL with entire scope across all datasets. I think maybe this phenomenon can be attributed to that the scope of heterogeneous is more accurate than the scope of entire. So let's move on to the hyperparameter analysis part. We can see for all 4 datasets, the optimal hyperparameters of NLGCL are similar, which could potentially reduce the cost of hyperparameter graph search. Actually, we always provide some insights about how to choose hyperparameters for NLGCL in different datasets, in different data sparsity level, but you can see this part in our original paper. And we also talk about the efficiency analysis in our original paper and some extra experiments like visualization for the representation, and also talk about some future direction for this paradigm in our paper. The code can be found in this GitHub link, and feel free to reach me about any questions. That's all. Thanks for listening.
What ensures these views remain semantically rich enough to provide effective contrast? Can those end up being too similar across layers?
Actually, I think this problem can be understood as what is important things in our NLGCL for its for our performance improvements. Actually, I think the most important thing is our multiple high-quality positive pairs. Existing GCL methods always build one positive pairs, and maybe the contrastive views need some data augmentation operation, and the data augmentation operations may lead some task irrelevant noise, because we need to use some like feature perturbation, like structure perturbation to build these contrastive views. And our NLGCL mitigate this negative impact. And also, one interesting thing is that a recent paper accepted by other top conference also found the same observation in general contrast learning field, that multiple positive pairs can achieve higher performance than only one high quality positive pairs.